So there's no good way to break up 7-2, so we're just doing all of it today, and it's like only 20 minutes, so it's not terrible, but a little longer than the last 2 days since we broke 7-1 up quite a bit. All right? Sample proportions. So what proportions of U.S. teens know that 1492 was the year in which Columbus discovered America? What did you say? Right, exactly. A Gallup poll found that 210 out of a random sample of 501 American teens aged 13 to 17 knew this historically important date. Not good, people. So p hat, that's one p hat, one sample proportion. So clearly this wasn't at our school, right? Only 42% knew the answer to this out of 501. So that is a p hat. Yes. What page are we on? 440, I think. So this is the statistic that we use to gain information about the unknown population P. Remember that this guy's the statistic, whoops, the P hat, right? That's one sample, and the true P is a regular P without hat. All right, so if we were to take a different estimate at Devlin, hopefully we would get a different number. But anyways, we're going to learn how close is close as we go through the rest of this chapter. All right, sampling distribution of p hat. Activity, the candy machine. So we're going to read through this and do it as we go all together. So Kim, will you read the first paragraph and number 1? All right. So you guys, we've got the probability of orange candies. We're going to change that true proportion, our true P, to 0.45, right? And we're going to go back to the rest of this. All right, and so we did that. Number 2, Haley, what's number 2 say? All right, so we're going to draw 25 candies, and I'm going to draw 1 sample. So there's my little candy machine going. And we got 60% that were orange. So out of 25, however many that is, 60% are orange. That's 1 draw. How close is that to 0.45? Not super close. All right, and then down here they're plotting that 1 little dot. That's 1 little p hat right there. Okay? All right, Elizabeth, read the next part. All right, we're going to do 9 more samples. So I'm going to put a 9 in here and draw samples. And so it's going to go through. We got a 0.48, pretty close to our true P. A 0.4, 0.32, 0.32, 0.36, 0.4, 0.48. Pretty exciting. Okay, good. There's our little dot plot down there. So, Brady, what would you guess like the mean is from looking at the graph? Where's kind of like the center? Around 0.4. All right. And for the standard deviation, do you guys know how we could actually find the standard deviation? The formula we just learned, right? Square root of p times 1 minus p divided by n. P would be our true P. What's our true P in this problem? 0.45. And what's our n in this problem? We're drawing 25 each time. Okay? Cool. All right. And the next one, Pat O. What is the next one? Number 4. All right, so I'm going to take animate off so this doesn't take forever. We're going to do 390 more samples to get a total of 400. Boom. Look how fast that did that. All right. Our dot plot has a ton of p-hats, right? There's 400 little p-hats, each with a proportion out of 25 that were orange. Does this look better than our last graph? Yeah, it looks a little more normal. What's the mean of this one, you guys? What do you think? It is probably 0.45, really close to the true p, right? And how could we find the standard deviation? Use the formula, okay? So it'd be similar. Alrighty. Oh, and by the way, it says to do socks. Are there any outliers, you guys? Probably not. You think there is? This guy right here? Okay, potentially this one. You could say that. Is it symmetric? Yeah, roughly symmetric. All right. Number 5. Let's go. Melissa, what's number 5? All right, so this time instead of drawing 25, we get 50 candies each time. We still are going to do it 400 times. Boom. So it's hard to tell without really looking too carefully. However, what did we learn yesterday? If we increase our sample size, what happens to the spread? Decreases. All right, so it's still symmetric. There's probably not any outliers. The center is still 0.45 on this, but our spread would change. All right, we increased n, so our standard deviation should decrease. And when we do the formula, what do we plug in for n now? 50. So we're dividing by 50 instead of 25, which makes sense then that the standard deviation decreases. Okay, so there's less variability. Yay. Number 6. Alexis, will you read number 6? Let's investigate. So I'm going to change this so the true number of oranges in there is only a proportion of 15%. And I'm going to change this back to 25, maybe. There we go. And I'm still taking 400. Does that look symmetric? Kind of. I don't know. Right? A little less. It's a little more questionable. Did it tell us to do 400? Yeah, I guess it didn't really tell us. I'm going to do it one more time. Okay, could be a little skewed. Not really sure. But, yeah. Now let's try 50. Still looks a little weird. Okay. So this has to do with normality that we learned, you guys. It says to like investigate it, but we did this last semester, and so I just am going to remind you instead of investigating it. So remember to check for normality. Anybody remember what that formula was from like chapter 6? I didn't think so, but we'll do it anyways. N times p greater than or equal to 10. N times 1 minus p greater than or equal to 10. This is called large counts. All right? So if you don't have greater than or equal to 10, you're not necessarily going to have a normal distribution, which would be like symmetric bell curve. So like when I had n was 25 and my proportion of orange candies was 0.15, we don't get a big enough number to make it normal, okay? And then we would have also had to check this times 1 minus 0.15. Whoops. Okay, Okay, so 25 times 0.75 and see if we get greater than or equal to 10. So when you increase it to 50, your chances are better of being greater than or equal to 10. And when we had 0.45, that helped as well, right? So you always have to check that in order to know if you have a normal curve instead of just a bunch of dots that could be skewed. Okay? So whenever NP and n times 1 minus p are at least 10, a normal distribution can be used to approximate the sampling distribution of p hat. We will do this a lot more the rest of this year. All right, take good notes on this. So sampling distribution of a sample proportion. What's the mean of all the little p hats? Okay, mu of p. So this symbol right here, if you can't read it, says mu of p. That is the mean of all the p hats. So taking a whole bunch of samples in a proportion, we're talking all proportions today, and if you take enough, then the mean is just equal to p. And what is p? It's the true proportion, right, with no hat. So you shouldn't have to think too much. If I do enough of those, then mu of p hat is equal to 0.45. Like it was in the Reese's problem, right? That was the true proportion. And then we have the formula I showed you guys the other day. So the standard deviation, sigma p, use this notation now, okay? So sigma of p hat, that's standard deviation of all my little p hats. So I'm taking a bunch of proportions, sample proportions. Square root of p times 1 minus p all over n. And you're going to have to start checking the 10% condition with standard deviation. Anytime you're doing that standard deviation formula, check the 10% condition. N is your sample size, less or equal to 1/10 of your population size. Okay? Why do we have to check that? Well, it has to do with independence. So, the formula for standard deviation is exactly correct only if we're sampling from an infinite population or with replacement. So if it's infinite or with replacement, it's exactly correct. A lot of times we're not sampling with replacement, so then you check the 10% condition, and as long as that is true, it's close enough. I would probably just check it every time if you're not sure. Then check 10%, and you'll be good to go. Okay? And of course, we have what's called large counts. So 10% condition goes with standard deviation. Large counts shows us something is normal. So if you're going to use normal calculations, you have to check large counts. Okay, n times p greater than or equal to 10, n times 1 minus p greater than or equal to 10. Tells us if it's normal. Yep. All right, about 75% of young adult internet users ages 18 to 29 watch online videos. Okay? Suppose that a sample survey contacts a simple random sample of 1,000 young adult internet users and calculates the proportion p hat in the sample who watch online videos. What is the mean of the sampling distribution p hat? So the mean of the sampling distribution, mu of p hat, and I would write these down. It's like one little thing, so you guys are zoning out here. Mu of p hat is equal to the true p. What's the true percentage of people who watch online videos ages 18 to 29? Yep, so that was easy. That's all you have to do. Okay, mu of p, all your little p hats should be equal to the same thing as the claim. All right? And now it says find the standard deviation of the sampling distribution p hat. Check the 10% condition. Anytime you do standard deviation, check the 10% condition pretty much. All right? So first I'm going to check 10% condition. N is less than or equal to 1/10 of n. What's little n in this problem? We took a simple random sample of 1,000 people. Is less than 1/10 of. What's the population in this problem? All 18, 29-year-old internet users. How many of those are there? A lot, all right? in the whole entire whatever, it doesn't specify even US. So there are a ton of people that are 18 to 29 and use the internet. So is this true? Is 1,000 less than a tenth of all internet users? Yeah, okay, probably. And now we can do the formula for standard deviation. So I've got sigma p hat. That's important, this symbol. You're going to lose points if you don't have it. All right, square root of. Charles, what's p in this problem? Oh, good, 0.75. Cadence, what's 1 minus p? It is 0.25 divided by n. Mitch, what's n in this problem? There's no way to plug in infinity. It's definitely the little n, right? So 1,000, it's our sample size. And press enter, get that in your calculator, we get 0.0137. What does that even mean? It's the typical distance from the mean. Our mean is 75%. We're going to typically be off by 1.4%. Okay? That's your standard deviation. Is the sampling distribution of p hat approximately normal? Check the large counts conditions. So in order to tell if it's normal, we have to do n times p greater than or equal to 10. My mouse went away. Oh. All right. N times p greater than or equal to 10, or n times 1 minus p greater than or equal to 10. Okay. Pete, what's n in this problem? It is still 1,000, yeah. And Patty, what's p in this problem? True, p is 0.75. That's 750. You guys, you have to actually calculate this. Okay, 750. Yay, that's greater than or equal to 10. All right, we still have 1,000 over here. 1 minus 0.75 is 0.25. That would be 250, which is greater than or equal to 10. So can we use normal conditions? That means we can use our calculator and do normal CDF now, okay? You will always be checking that first before you do any kind of normal calculations for proportions, okay? What if the sample size is 9,000 rather than 1,000? How does this change the sampling distribution? So remember, if we increase n, what happens to our standard deviation, guys? It decreases. So instead of plugging in 1,000, we can now change n in our formula to 9,000. Same formula, right? Here's what they did, though. They plugged in 9,000. And what happened to this number? It decreased. Our standard deviation decreases when I increase. You're going to have to know by what factor it's actually increasing or decreasing. So how do I know? Well, I had 1,000, right? This is times 9, but there's a square root there, so the square root of 9. So we're really decreasing by a factor of 3. Okay? All right. Now let's actually use normal approximations. So the whole point of that, you're going to go through that process a bunch of times where you check 10%, you find the standard deviation, you check large counts, then you know you have normality, and then you actually do the problem. Okay? Now let's do a probability problem. Going to college. A polling organization asked a simple random sample of 1,500 first-year college students how far away their home is. Suppose that 35% of all first-year students attend college within 50 miles of home. Find the probability that a random sample of 1,500 students will give a result within 2 percentage points of the true value. So I'm finding a probability. I'm within 2 percentage points of the truth, right? How many college students are in between there? So 33 would be 2 below. I want my p hat to be in between. And then if I go to above 35, that's 0.37. I would write this down, those of you that are taking a little breather here. All right, we're going to need the mean and the standard deviation in order to use normal CDF, right? When you plug normal CDF into your calculator, we're going lower bound, upper bound, those two things. But then we need the mean and we need the standard deviation. So mu of p. Kelly, what would mu of P be? Exactly. It's the same as the true proportion, 0.35. All right, the next thing we would find is the standard deviation. However, you always check the 10% condition anytime you're doing the standard deviation formula. All right, so Matt, what is little n in this problem? It is 1,500. And Bert, what's the population we're talking about in this problem? Yep. All right, so 1,500 is less than a tenth of all. Yeah, that's got to be true, right? There's a ton of first-year college students. Another way you can do this, and the book's going to start doing this, is they're going to times both sides by 10, okay? And they're going to say, well, we've got at least 15,000 first-year college students, so we're good to go, okay? Same thing. Now we're going to do our formula. Again, this symbol is important, sigma p hat, standard deviation of all the little p hats. And our formula is p times 1 minus p divided by n. So Pat O, what's p in this problem? It is 0.35. And Melissa, what's 1 minus p? Yes, it is. Divided by n. Alexis, what's n? It is 1,500. Okay, we need this so we can use it in our calculator. We get 0.0123. All right, do I have normality? In order to use our normal CDF, we need to check large counts. All right, this is called large counts, and we got to plug it in. So Claire, what's n? 100. Yep. Kenny, what's p? 0.35. 1,500 times 0.35 is 525. So yay. All right, over here, same thing, 1,500, but this time it's times 0.65, 1 minus p, and that would be 975. And so yes, we have large counts, which means my graph is approximately normal. By the way, we no longer need a dot plot because I just proved it's normal. So if I'm drawing this proportion here, wow, there's a really bad normal curve, but there you go. Okay, right in the middle is 0.35. And I could do my standard deviations, 0.01. I'm just going to estimate like 0.01, so 0.36, 0.37. It's not going to be exact, right? But I'm just estimating. And we're finding the probability that that proportion, that P of my samples, is in between 33% and 37%. That's what we're technically doing based on what we wrote down right here, right? In between 33 and 37%. So I can do normal CDF. Don't forget, you have to label. So my lower bound is 0.33. And my upper bound is 0.37. My mean is 0.35. And my standard deviation, we use the one we just calculated from the formula, 0.0123. And we get 0.8931. What does that mean? About 90% of all the simple random samples of size 1,500 will give a result within 2 percentage points of the true proportion of the population. All right, so if we take a whole bunch of samples, about 90% of them are going to be within 2 percentage points of that 35%.